and will be sent to deep tea. Okay. All right. Welcome everybody. And so I'm going to be talking about compile time, reference counting, and lifetime analysis in Lobster. That's a lot of stuff. So this is a very informal talk, as you probably already know. So please interrupt me all the time. Tell me that I should be going faster or slower or whatever you feel like. I'm first going to give you a little bit of context. Is like, why should we care about this lifetime stuff? And oh, by the way, what's this lobster thing you keep talking about? And then I'm going to go into detail about the actual lifetime analysis. So first, let's take a step back, talk about memory management. I feel memory management is a great example of a design space where there really is no perfect solution, right? You improve something, you make something else worse. It has, in terms of its design space, a very multi-dimensional Pareto frontier that is very hard to advance. It's hard to make a solution in memory management that's everything to all kinds of programmers and all kinds of programs. Different kinds of programs require vastly different possible solutions that are good for a particular kind of memory management. I feel that like what kind of memory management you choose in a programming language has an enormous influence on the language. Yet at the same time, for most more average programmers, it's kind of an invisible thing that don't really think about too much. But that makes an interesting design space. I'm hearing someone. Or maybe someone can mute themselves, or I can mute you.
I will mute us. Did you kick Francis?
Okay. So let's see. We have one more person there. Is that Thomas?
Yes.
Okay. Welcome, Thomas.
That's a T.
All right. So, of course, when we talk about memory management, the number one kind of memory management that's by now used in pretty much most languages is, of course, the regular tracing garbage collection. It's kind of default when people think of memory management, or more importantly, don't think of memory management, is that's what's happening. It's been consistently nominated for Wouter's Least Elegant Algorithms Award many years in a row. By that I mean is like we're going to throw away any possible information or knowledge we have about lifetimes of objects in our program. And then once in a while, we're going to stop the entire program and scan all of our memory, or most of our memory, or some of our memory, and recollect that information, then do a bunch of cleanup, and then continue again. And for some reason, I'm really not a fan of that kind of thing. I think we should be able to do better. But of course, the reason why garbage collection is so popular is exactly because we haven't been able to do much better in other areas. So there are alternatives to garbage collection that are simpler but are quite limited in all sorts of ways. Of course, there's reference counting, which, as you all know, has limitations to being able to collect cycles, and there's a fairly constant overhead. Then there's, of course, everyone's favorite is to just do manual memory management. Don't have to go into detail about why that is problematic potentially. Then there is less known alternatives such as regions, linearity or uniqueness types, and various kinds of ownership models. I've implemented most of these, but in the past I've never thought that they were kind of like ready for prime time in terms of working with like regular programmers. But of course that last one, recently we've had a new challenger approaching. Yes?
Can you talk a bit more about regions, like as a overall scheme? Because I would think.
Okay, so regions, what effectively that does is you attach what's called a region to either, let's say, a stack frame or an object. And then while you're inside that function or inside the method of that object, you're saying any non-region objects that you're allocating get put in that region. And those can't necessarily be freed, they get freed together with the region. So it's kind of a mix of things. It means that
so it's like
you kind of need to think that like the lifetime of the objects that you put in the region are kind of the same as the region you put them in, and that works pretty decently.
Is there a distinction between arena? Is this like arena, or is this?
It's kind of like an arena. I guess you could call it arenas, but arenas are usually completely manually organized in a language like C++,
Yeah,
or
right.
something like that. This is the equivalent of that, but as a language feature in an actual programming language.
What is
Yes.
an example programming language that has this automatically?
A known programming language? No. Like all these types,
I see.
regions, linearity, uniqueness types, there are no, or even ownership, there are pretty much no mainstream languages use any of these things. We're talking purely research languages here.
No, even a research, I just wanted a name.
Yeah, I don't know one on the top of my head. There's a region version of Java, for example. Someone has made a Java that works with regions. Yes,
So-
Francis has an example.
Google's Sawzall is an arena-based model.
Oh, okay.
Google what?
Sawzall,
Sawzall.
the deprecated log analysis language.
It's still alive.
Of course, deprecated.
So, for example, uniqueness type, I know the one of the most well-known languages is called Clean. If you know functional programming language, you may have heard of this language. But of course, there's been plenty of ownership-based languages, but none of them have ever gone anywhere until recently, when we've had Rust. And Rust, of course, gives us compile time memory management, which is really, really cool, with some possible escape hatches. To a certain class of users, like people that are fed up with C++ maybe, it appears to be like a fairly optimal way of doing things. But of course, there are downsides. It requires quite excessive amount of thought put into ownership, borrowing, lifetime annotations, that for the average programmer that's currently enjoying a garbage collected language is probably a little bit too much. Even if I think that that would probably be healthy for them, but they probably wouldn't want to spend all that time. There's other problems. If you go to more complex data structures in Rust, you'll end up using many of these escape hatches. I looked at some point into like how do people do tags or graphs in Rust, and I read quite a few blog posts, and some of them were like surprisingly bad. It's like, well, we just use indices, and it's like, well, if you use indices, then how do you delete an element, because you would need to renumber these indices or something like that. Well, we don't delete elements. It's like, well, that's not a very good implementation of a graph, people. It's like, GC languages do that much better. So, there's downsides there. But I think the important thing to take away from Rust is that it has demonstrated that it is viable to have a compile time memory management. So compile time memory management, thanks to Rust, is a thing. So now we can start thinking about like, well, how can we potentially do better? So of course, that's what I want to talk about. To me, there is clearly a wide open design space between Rust, which is very, very exact and picky on like this compile time management on the one hand, and you have these friendly garbage collected languages that don't have you think about this stuff at all. Somewhere in between, there's possibilities to do better. Can we somehow combine these two extremes to something? And then I have to bring up what I mentioned before, my idea of a Pareto frontier. If you just think of memory management along two axes, where one you say is like, well, how easy or hard is it to deal with memory management in these languages on the one axis, on the y-axis, and on the other axis you say is like, well, when is lifetime management actually happening? So just completely happening at runtime or completely happening in compile time. And if you do that, you get like, the usual spots, of course, with dynamically typed languages are extremely much about runtime. Then you have your average garbage collected language like C#, Java, Go, and Swift that are mostly still everything at runtime, have some static features. And then all the way over in the corner, we have Rust, where you can do pretty much everything at compile time. But in terms of ease of use, we're like way up the chart into the corner. Just for fun of it, I put C++ on there, which I think is inside the Pareto frontier because it definitely doesn't do quite as much or as well at compile time as Rust, but is at least as complicated, so therefore kind of loses out. But the big question to me is like, where those question marks are. Is there something that is mostly compile time like Rust, but retains a lot of that ease of use of these other languages? Well, of course, you already know the answer. and I've already implemented it, and it's called compile time reference counting. So before we start explaining what that actually is, I want to remind you very, very briefly, what is this Lobster thing this guy keeps talking about? So it's my friendly pet programming language. It is mostly not a Google project, even though I've occasionally used it inside of Google. I'm not going to describe this language in any detail whatsoever. I'm just going to mention a couple of things about it that are relevant to the topic of compile time reference counting. So first, what was the memory management scheme of Lobster so far? So far has used, the main scheme is to use runtime or old-fashioned reference counting. In addition, I've added leak detection, means at the end of the program, you get a little report saying it's like, hey, there's these objects have remained deallocated at the end, and you should probably do something about that. And that's meant to help programmers to manually insert assignment statements to clear back pointers. That has that works pretty well in the sense that the amount of times that you have leaks because of back pointers doesn't happen that often, and when it does happen, this report makes it very, very easy for you to find like where to fix that. Beyond that, reference counting does have a surprisingly high constant cost, as some of you may know. The other thing that Lobster does is have inline structs. So of course, the best way to reduce to have efficient memory management is to not do that memory management in the first place. So these inline structs are inline to their parent. They are immutable. They're always copied. Besides being very efficient, this is also important for lifetime analysis, because basically in all these copied objects, they are effectively invisible to the lifetime analysis algorithm. So they reduce pressure, if you will, on how many objects cause lifetime issues or dependencies, and therefore make the lifetime analysis algorithm more likely to succeed without any errors. So that's pretty cool. So it's very efficient. It has similar zero-cost abstraction properties as you have in C++ or Rust. And it's kind of essential to have, especially in a language like this that is used for games and computer graphics. So you have all these 2D, 3D vectors flying around everywhere that you don't want to be heap objects. So a little bit about a type system as it relates also strongly to this algorithm. So typing, strongly typed, it has this kind of whole program, closed world model, type inference, so it really knows a lot about what's going on. It does automatic specialization of functions. So in C++ synthesis, if you have templates everywhere, which sounds terrible, except in this language is more high level and not quite as complicated as C++. So it's actually quite manageable. It's completely flow sensitive, which means the type checker always knows the context of what it's type checking in terms of the call graph. And that means it can be smarter about like what types to assign. It knows about whether things are non-nil and things like that. It knows about not to type check dead branches, which means it has similar properties of doing if const expr in C++, which only recently appeared. So you can do much more with this type system than most languages. The type system is important because the lifetime analysis algorithm that I'm about to describe is actually integrated with the type checker. Now that sounds kind of like a terrible idea, because you probably would want that to be in a separate path or separate algorithm, and that is true. But it turns out that this flow-sensitive specialization that the compiler does, that these decisions taken there need to be taken into account both the type checking and the lifetime analysis. They kind of need to work together to make the best decisions there. So they kind of have to be part of the same algorithm. And if I would separate them, I would have to duplicate a lot of logic. So I just decided to like, oh well, let's just mix it all in one.
You said something about making the best decisions. I was wondering if you could elaborate more on that. Like, what did you run in? Like, I think you said something about, okay, it makes the logic simpler. It makes like, can you elaborate a little bit more?
And I have a slide on like an example of this, but the short of it is that you basically also want to specialize on lifetimes. So if you call a function currently specialized, if you call a function with different types, it makes a different specialization. But now if you if you call it with the same types, but these types have different lifetimes associated with them, then it's also going to specialize.
Okay.
And I have a slide with
kind of
more details. Sorry?
Kind of a hierarchical specialization of.
Yeah.
Okay.
Yeah. So it takes types into account, takes lifetimes into account, and takes free variable, takes a whole bunch of things into account, whether to make a specialization or not.
Okay. I'll wait for your slide.
Yeah, I'll get into slightly more detail about like how that works in a bit. So effectively what the algorithm does is, of course, it designs for every allocation made who owns those allocations. It assigns either owning or borrowing semantics to each AST node and variable, and it all happens in a control flow sensitive way, much like the type checking. So these algorithms are extremely similar. In fact, they are related. So the special thing about this algorithm, very much unlike Rust, is that it's completely automatic. It does not require any programmer intervention. There are no annotations required to tell like who you want to own or what lifetimes you want or any of this kind of stuff. That's kind of in line with the design of the language in general. As you maybe have seen in a past talk by me, is that the type system is also very much about allowing you to write code as if you're writing in Python or something like that, and then magically get static typing out of it. So this design of this algorithm is the same. It's meant to allow you to program as if you're using a garbage collected language, and then boom, ooh, it has the same kind of properties as something close to Rust. Is kind of the goal of all of this. It actually works. I had a large body of pre-existing code before I started this particular algorithm, and I was able to write this algorithm in such a way that there were only in about 2 places in the code where changes needed, and everything else just compiled and run correctly without needing code changes. So in that sense, it's a very honest test. If you first design a feature and then write the code to suit it, then you don't know whether you made any accommodations for it. But here I already had the code, assuming that there was just runtime reference counting, and now it works with compile time reference counting, just as is. So it's cool. Doesn't require the programmer to know that it's using this particular feature. And if you remember my Pareto frontier example, I think that makes a huge jump up from Rust in that sense. The catch, I said, is compile time reference counting. It still has an escape hatch to runtime reference counting. If it can't, for whatever reason, decide that make something fully compile time. However, in the testing I've done so far, doing the runtime version of it only happens in about 3% of the time, which means that the cost of reference counting has been slashed by so much that it pretty much trying to optimize the remaining 3% is not super worth it. Because that 3% means that you do get to mostly ignore that you're using a compile time reference counted language, which is pretty cool. In the future, I want to allow programmers that want to selectively say is like, I want this value or this function to exclusively own these things, and rather than insert a reference count increase to just basically error out, much like Rust does currently, if they want even more control over memory management. But I think for most programmers, it's completely not necessary. So how does the core of the algorithm work? Basically, what it does, as it's doing its flow-based type checking, it's going to match the lifetime expectations of the children. Children say whether they want to be owned or borrowed with what the parent wants, like whether they want to own or borrow the children, and then tries to match those as best as possible. Of course, if those two sides agree with each other, then nothing happens, no runtime costs. So a simple example of that is I'm allocating a data structure, like here, a little simple vector, and then assign it to a variable. And the variable says like, hey, I want to own you, and the data structure says I want to be owned, and they're both happy, and that's all cool. Now, what's of course interesting will happen when there's a mismatch For example, if the parent says, I want to own you, but the child says, like, I would prefer to be borrowed. For example, in this example, the B says, I want to be borrowed, and A says, I want to own you. So there is a clash there. And by default, what happens here, that a reference count increase gets inserted. Now, this situation apparently doesn't happen that often in code. And like I said, optionally, at some point in the future, this can also be an error if the programmer desires that to be an error. And the opposite situation is, of course, if the parent wants to borrow, but the child wants to be owned. In this example here, for example, most built-in functions like print or whatever, they don't need to hold on to the value. So they want to borrow whatever argument is being passed to them. And of course, the data structure requires that it's being owned because there has no other way. The solution here is to insert a anonymous variable, effectively, very similar to how R values are being handled in C++. So there's an anonymous variable, then print will then borrow that anonymous variable and is happy. And then at the end of the scope or whatever, that anonymous value gets cleaned up.
Is there a difference between the borrow ownership /ownership and L values and R values, or do those concepts map pretty exactly? Like, are there any R values that want to be owned, or any R values that want to be borrowed, or L values that want to be owned?
They map mostly close. Well, I guess it's a little bit different from C++, because I'm saying like R values in C++, that's not quite correct, because these things are always pointers, always by reference, whereas an R value that needs to be stored in a local variable is because it's being passed by value. So that comparison is maybe not that great. I'm only mentioning that because basically what C++ does when it has when you receive an R value back from a function or something like that, it creates effectively something like a local variable for you. And that's exactly what's also happening here. But the concepts are not quite the same. Does that answer your question?
I think so, yeah.
So let's talk about L value borrowing. So that's a little bit more complicated than the average value. So by default, when we have an LVO variable somewhere being used, they want to borrow, since it's already owned somewhere else by definition. So what we do in the implementation, we track all active L values. We compile time reference count these to track how many borrows there are outstanding to them. And as these values get consumed by operations, this reference count decreases. And if you're trying to mutate this particular L value while there are borrows outstanding, you get a compile time error. This is pretty similar to what happens in Rust. In the future, we may also want to support L values that are borrowing just their initializer. Turns out that makes the algorithm a ton more complicated, and it's kind of diminishing return in performance in terms of how often that is reducing the amount of runtime reference counts. So I haven't done it so far, and I might never do it. It seems to work pretty well so far. L value typically ends at the end of the scope, but it may also end in a last use of that variable if we can safely analyze that the last use is always in one particular location. So for example, a function ends with like return A, which is a pretty common pattern, then rather than normally return would increase the reference count of what it's returning, but in this case we don't do that. We say it's like, well, we're actually borrowing A, and ignoring, we make it go out of scope, like right here, basically. That is currently quite limited in terms of in what cases it does that, but that is intended to be expanded in the future. Okay, so here we are.
Can you explain the return thing a little bit more? I think I'm missing something, because you don't want the value to end at the return. You want it to end at the thing that's consuming the return or
So
something.
you're ending it within that scope, right? So you're effectively moving it out of that scope.
I'm saying that by default, if you do things at the end of the scope,
Mm-hmm.
then you'd be holding on to what's effectively compile time, like one reference count
Mm-hmm.
until the end of scope.
Mm-hmm.
But then you do something like a return A. Currently, it's such that returning something from a function wants to own the thing that it's returning.
Mm-hmm.
It could also borrow, but that's, again, more
Okay.
complicated. So
Yeah.
that's currently what it's always
Okay.
doing. So the naive version of this would say is, so if you do return A, the thing is still live, and therefore I'm going to reference count increase so that it can be returned, and then it needs to decrease it at the end of the scope.
Oh, okay.
So effectively what it does is just say, it's like, okay, in the cases where return A is always the end of the function, I'm just going to cancel those out against each other. And I'm going to artificially make the lifetime end like a little bit earlier than it normally does.
Okay.
So it's purely an optimization, but it's an important optimization because this kind of code happens all the time.
Okay.
In fact, when I made this optimization, I saw like a big drop in the amount of reference count increases that were needed in it.
Okay, I think it makes more sense if I think about it as like the implementation where you're saying, okay, we're just doing this per scopes, but then return is
Yeah.
effectively ending the scope.
Yeah.
Yeah, okay.
Yeah. So it's a little bit cheating, but it's fine because we know that there's nothing that can come in between those two spots.
And this is essentially because return wants to own, right?
Yeah, and that's another thing. That's a limitation currently. And again, that was a decision I made to keep, like initially I kept things simple. It's like, okay, I'm going to return functions always owning. There are situations where having a function return something that's borrowed would also be cool, but I haven't found a reason that that's greatly improving the amount of the performance of the average program. So that may be something I might look at in the future. So.
But yeah, but from a mental model standpoint, though, like because return wants to own, it has to.
Yeah.
That's where it would increase.
Yeah, if you just do, for example, you return of some new data structure, then that's very natural because it wants to own it and it's brand new right there, so there's no reference count increases happening there. But with a variable, at least conceptually, it keeps on living after the return. And of course, it might do if the return was conditional or something like that. So. If the return is conditional, it will result in a reference count increase in the current implementation.
What happens if you have a let binding and you return a function defined within like a free return one of the values?
Lobster does not have closures as dynamically allocated objects. They're all non-escaping closures.
So you can't escape then. You can't escape.
You can't escape closures, yes. That is on purpose. Closures are all maximally efficient in this language. So here we get to like one of the more interesting things. This is what DeepT was referring to earlier, is that this language is very much centered around this idea of specializing everything when needed. So it is nice if we can have the caller and callee agree on lifetimes. Then of course, not only is that more efficient because there is less reference count stuff going on, it also increases the total amount of code that can work error-free. In the sense that if you force something to a lifetime that some code doesn't want, then that may cause an assignment to suddenly blow up because now it's trying to assign to something that's borrowed or those kind of things. So it's doubly important, both for efficiency and in terms of the amount of programs this can handle without erroring out. So that's why we decided to specialize on lifetimes. A super simple example is here. So you can call a function f with two arguments, one that very clearly wants to be owned, that's the first one, and the second one that very clearly wants to just borrow. And if you didn't specialize, you'd have to choose one or the other and make the other therefore less efficient. Now, this example, you could probably say because print typically wants to borrow, you should just borrow in all cases would be slightly more efficient. But you can't say that in all cases. If the body of f is more complicated, then you cannot compute that property ahead of time, especially since the order of type checking goes from the caller towards the callee in that order. So we don't first type check f and then decide what to do with the arguments. No, we first type check the arguments and then go type check f in a specialized version. There's some exceptions to when this happens. Signed arguments currently always own. That just seems to work better. Coroutines, because they actually exist after the function has returned, typically to own all their variables, and as we saw, return values. But some of these may be relaxed in the future. Here's some more examples of other kinds of AST types, like what they do in terms of owning, borrowing. So where is assignments, they want to own the return value of the overall assignment is still a borrow. If, of course, as you can imagine, does a union of both branches, hopefully those two things are the same. If they're not the same, it will default to own at the moment, simply because own is a slightly safer union of two differing branches. And an OR a little bit interesting because they function mostly like an if then else, but they have special properties. Like, for example, if you do something like A and B or C, then the value that is A will never be the result of the whole. It will only ever be B or C. So therefore, it is even more lenient than an if then else could be. While borrows with condition, that's not that interesting. String contents are actually pretty interesting. I found that the vast majority of users of string contents, the recipient wants to just borrow this string constant. But of course, conceptually, string constants are created anew, so they're like an allocation. So what I did is, implementation-wise, string constants are now treated as if you put them in an anonymous global variable, and then you borrow from that global variable. And that reduces the amount of reference count increases around string constants a lot. Most operators only work on value types, so they're not that relevant to lifetime analysis, except for something like plus on strings, which borrows its arguments and then results in an owned value. Most built-in functions by default, they borrow their arguments and then return something owned. So for some of them that's flipped. For example, if you have push, whose first argument is a vector, and then the second argument is what needs to be pushed in there, is very similar to an assignment that it wants to own its second argument. And then our return we already talked about. So it typically wants to own and has exceptions for things like a single variable. So just some examples, but I guess the takeaway from this slide is that the core of the algorithm is actually pretty simple, right? It depends on this ownership matching of parent and child, and then the specialization. That's the core of the algorithm. But then the details are complicated because every AST type has a different way in how it interacts in terms of owning and borrowing with its surroundings. And figuring all that out was actually the bulk of the work, if you will, to getting this all working. So let's talk about the possible new errors that you can get. So the most real one that you could possibly get is cannot assign to X while borrowed. An example of this here, we allocate a new X that we own, we pass X, borrowing it to Y. Y is a borrowed variable. Now suddenly we overwrite X, and while it's being borrowed, and that would deallocate hello in this case, and then you try to print Y and you're referring to a deallocated value. That of course couldn't work. So in this case, you'll get the error that you can't assign to X. It turns out that, at least in all the code I've written so far, it's pretty uncommon for code to be modifying an original value that you borrowed from. Because usually when you borrow from something, it's because you want to access that value through the borrowed variable and not through the original variable. This is pretty contrived code in that sense. It only occurred once in all the large amount of code I had, this situation. So it's not really a big deal. I've never run into this. And then there's more errors, and these occur even less. In fact, the last two, I've never even ever seen them. So cannot assign to borrowed argument happens currently with dynamic dispatch, because then the arguments have to agree, but again, it doesn't really happen. The last two are just an indication of my failure to do a formal proof that my lifetime analysis is sound. If I knew that my both design of my algorithm and my implementation were correct, then I could turn these two errors into asserts. But I'm not that smart, so there's still errors, but I haven't seen them appear. So that seems to be working pretty well. Maybe at some point that can happen. So, conclusion, we have a non-intrusive, easy way to use memory management with potentially the efficiency of something close to Rust. I would argue this is maybe close to optimal, but maybe you guys have an opinion about like where else in the design space you think things would be optimal. I'd love to hear that. So, if you have questions about all of this, and of course, if you want further information, there is stuff out there.
I have a question about, so you're saying the built-in functions, some prefer some arguments to be borrowed or prefer some arguments to be owned. For user-written functions, can they make declarations like that? Like this argument prefers to be owned or borrowed?
Yeah, that's the fun thing. You currently can't. So, because basically user-written functions are typically, because there's no lifetime annotations, that means that basically the programmer saying, I prefer this thing to be owned is actually, I don't even know a situation where that would be useful. Because basically, if a function calls you in a way that you didn't intend to be used that way, you just get a specialization, and it'll work.
So if I like implement my own vector and I'm implementing push, then the compiler will just figure out that it needs to make like an owned. Like when I push an element, it needs to reference count that element, or
not even. If you have your own push function and you get callers, one of them gives you something that can be owned and the other gives you something that can only be borrowed. You may get two implementations of that function, and the function where you're getting something that's borrowed, which is not what you intended, will then cause that second specialization to have a reference count increase just before you actually put that element into your vector.
I see.
So
that would
be
end
slightly
up
less optimal, but at least it will do the correct thing for all the possible callers.
I see.
And you could, maybe at some point you can introduce that. You could just force that to be owned, or maybe documentation-wise you might want that. But again, my first challenge was to see is like, can I make this completely automatic to the point where, an average Java programmer or whatever can jump in here and not be confused. And this could be added optionally in the future, but I've not seen a strong use case for that yet.
It seems like as a user, it would be very difficult for me to figure out whether or not something's going to be owned or taken as a reference, and if there's going to be a reference count increase involved with it. But maybe that's working as intended.
Yeah, but that's also what I said is like I have intentions for programmers like yourself who like Rust to at some point have an optional way to say is like I want to force this to be owned or borrowed in this way, and I want to basically avoid a reference count increase from happening. And then when the lifetime analysis algorithm is going to insert a reference count increase, you'll just get an error, and then you'll have to work around it. And for some code that might be, for example, you have a tight loop, and you just want to make sure that in that loop, the data structure that you're working with, there's no reference count increases in that loop. Currently, you cannot avoid that. It typically does not happen. But yeah, I want to give programmers the opportunity to avoid that in the future. But like I said, it's like, given that I so far have measured that like the amount of reference count increases that are in a program are like 3% of what used to be there, it doesn't seem like it's an urgent issue.
For your specializations, I have two questions about that. What are how many points of specialization for a function exists? Is one for every variable? Like it could specialize it could generate independent copies. If you have a function with x and y,
Mm-hmm.
it could have one with x borrow, y own, x borrow, y borrow, x own, y own. Like you just have the whole matrix. You could specialize that. And for, I don't know much about the language, but the closures cannot escape, but there are closures. So for closures, for closed over variables, it also has like 1 point for each of those.
You say 1 point, you mean like one possible
Like, can I generate a
specialization
new
variant?
copy if there's an owned versus borrowed difference for?
Yes.
Okay, so naively, that seems like you could really blow up in code size. Have you observed that in practice?
Well, that's already with a type system, you can potentially have that, right? Because
If you have automatic
I have 5
specialization.
arguments, I can have 32 possible specializations right there. That typically does not happen. Like in tests I've done so far, like typically I see about like a 2x blow up versus the original code in terms of the total number of AST nodes. And then what you get is that because you're specializing so much, like the amount of functions that drop to like just having one caller increases a lot. Those then all get inlined, potentially get reduced in their AST counts as well. So in total, the total amount of bloat in terms of like extra AST nodes seems
Well,
to be
is this
quite reasonable.
is this a compiled language? Does it compile
Yes.
down to something to machine
This
code?
is all strongly ahead of time compiled static
What is
language.
the what's the end blob that's generated? Is it machine code? Is it bytecode?
There's currently 3 backends. There's a bytecode VM, there is a C++ backend, and a WebAssembly backend.
I see. And then for code size for those backends, you didn't really observe anything going haywire.
Well, those are very. I mean, there's like that has like a linear relationship to the size of the bytecode or the AST.
Okay.
Once I know like the AST is 2x, bytecode tends to be 2x, C++ code tends to be 2x.
Okay.
That is all. C++ code is pretty big, I have to admit, really, but nothing problematic so far. Nothing Clang can't chew through.
So what happens when there's a graph? I guess it falls back to reference counting.
Yeah.
So does that mean that you only had 3% of code that's graphy in those code bases?
No, the 3% is like how often it happens at runtime. So it doesn't mean it's basically just count the total number of reference count operations that happen during the runtime of a program, and that dropped to like 3%. It does not say anything about the total number of reference counting operations that are present in the program, which is still maybe a lot of, but as long as those are not being frequently executed, that's all fine. So yeah, complex, hairy code tends to have reference count increases, but as long as those don't end up in inner loops and frequently executed code, that's all cool, as far as I'm concerned. So yeah, more complex data structures will typically have reference count increases. Yeah.
I'm going to ask a dumb question. The
Yay!
compile time reference counting.
Yes.
What is the thing that is happening at compile time?
The eliding of the reference counts, right?
Yeah.
So if you can figure out that this thing does not need to have a runtime like
Component to its lifetime.
incref,
Yeah.
it lies in that
So
code.
basically, the old code was such that like every time you load a variable into stack, incref. Every time that variable gets dropped somewhere, decref, right? That was like blindly being inserted throughout the AST everywhere. So now we have this algorithm which just says like, well, we're just going to not emit these things unless I see that I'm going to have to increase it because we have this clash of someone wants to be owned versus someone wants to be borrowed.
And then
So imagine it that it's like, it has these points of emitting these increfs, decrefs, and rather than them being blind, there is this conditional in front of it that says like, do we have a clash here and do we actually do this thing? And most of the time it returns, no, we don't need to emit it.
So in the case of an object needing 0 runtime things, runtime reference counting operations, at what point does it get deallocated at the end of the scope? By like there's some insertion, there's some code that's emitted to deallocate it in the scope.
Yeah, that's a typical example. So you'll have data structures being allocated, gets put into its single owning variable, then gets used all over the place. None of that results in increfs or decrefs, and at the end of the scope, gets
Whereas
deallocated.
previously, in a purely runtime system, it would get deallocated the minute the last decref gets gets executed.
It would typically, well, it depends. It could also be deallocated at the end of its scope, but that happens to be the last use of it. But the
It
difference
happens to be the last decref.
Yes.
Right. So with the move to compile time reference counting, are there any changes in, like, have you artificially shortened or extended lifetimes because now you've moved where the allocation happens?
I have artificially, no.
Because I remember things from Java, if you try to do things like, if you try hard to do with escape analysis and stack allocate a bunch of stuff, you sometimes end up artificially extending live ranges. And you kind of defer to the allocation until later than it would have otherwise happened dynamically.
Like if you had like 1,000-line long function and use a variable in the first 3 lines.
Whereas previously, like, you
In the 4th line, you would get decref, and but now it waits.
maybe something. I don't know the exact things. I'm just wondering, did it change the shape of the allocations and the deallocations?
I believe not. I believe that's still exactly the same. It is just aligning what's happening in between. I believe so. I'm not 100% sure.
For example, for a variable, it's probably like the variable like inks it, and then when deft it when the variable went out of scope.
Right.
Yeah.
Which is that
would be the same.
that's the same.
Yeah.
It's just statically determining where the last decref would be and then inserting the deallocation there. So it's the deallocation doesn't move, right?
Yeah. The deallocation was always there, basically. That hasn't changed.
But previously the deallocation was conditional inside the decref, whereas now you effectively inline it and make it unconditional.
It is actually still somewhat conditional in the sense that you can still, what you can do somewhere along the way, you can actually cause an incref, store that variable in some other data structure, make it outlast that own variable, which means that the cleanup code for that particular variable will not actually deallocate it. So there's still a test in there. If you cause increfs, then basically you can potentially cause it to not be deallocated there.
Right, but that's if you cause increfs. Like if you don't cause increfs, you know that statically now. That's the difference.
Yeah. Yeah.
Can you optimize out the field for the ref count from certain types?
That's a very good question. That is one of these future plans that I have. That could either be done by an analysis, because I know some variable never gets increfs, decrefs applied. But also, like I said, this more rusty mode where basically a programmer gets to say these kind of objects should never have increfs. Then it becomes easier, and I can actually align the ref counting field. Currently, for simplicity, all objects still have a ref count field. But that's a question of implementation optimization. Yeah, good point.
Could have a parameterized struct type that is like a ref of t. That is what models the ref type.
Yeah, the language is not quite that rusty yet, so.
More like in the implementation code gen side of things, but
yeah,
probably you would need serious code gen.
Is Rusty the correct? Like, I haven't heard it, but it sounds like it might be.
I have
the right
no idea
They might
whether-
not like it.
maybe that's extremely insulting to rusty programmers. So I don't know.
I've also heard rustic.
That sounds a little nicer.
That's a different etymology than rust, like the metal thing, though.
Yeah, I've heard both.
Maybe that's what they want. I don't know. I hope I'm not offending anyone.
So in Rust, I can have a vector of reference counted cells of some objects, right? So shared references or shared ownership. These things in my vector have shared ownership with some other part of the code. Or I can have a lifetime annotated vector of references where the objects are still owned by other parts of the code, but I have sort of like this scoped reference to them, and those are distinct. But it sounds like in Lobster you can't express the vector of references. You can only express the vector of reference counted objects. Or does your algorithm do some like more advanced analysis where it can figure out that all the elements of the vector have a limited scope and therefore none of them need to be reference counted.
No, it's certainly not that advanced. It's slightly different in those two cases in Rust, though, if I'm correct, because my Rust knowledge is not that fantastic, actually. In that, yes, if you had, for example, two vectors that both point to the same object, then of course there's no escaping that they will have a reference count of 2 for most of those objects. A big difference, I believe, with Rust is that if in Rust you make something reference counted with the reference count RC object, then you're basically forcing into doing mostly runtime reference counting. Whereas in Lobster, depending on how the analysis goes, something can either turn out to be compile time or runtime reference counting. So it can be on a per use basis, which I don't think you can do in Rust with RC. So that's like, in Rust, it's kind of like a cliff in the sense that you can mostly do things completely at compile time, you're guaranteed at compile time, and then use your escape hatch, and now you're actually ink-refing and deck-refing all the time.
So that's if you're using the escape ref hatch, which I think is like if you use a box object to actually get a ref.
Yeah. So typically most programmers try to avoid that, but I'm saying it's a big difference. Whereas in Lobster, you can have the situation where that just kind of happens on a per use basis and automatically gets optimized for you.
I think Thomas is asking about like if you have like a vector of ref objects that aren't like boxes, they're
Yeah, the lifetime annotations, yeah, the Lobster has no equivalent to that, no.
Right.
So that allows Rust to do certain kinds of situations that would otherwise not be expressible. And yeah, Lobster has nothing like that.
Right. So the equivalent in Lobster would fall back to using runtime reference counting, where with the Rust annotations you could avoid that.
Oh yeah, I'm sure there are situations where it's still compile time in Rust and Lobster currently does a reference count increase. Yeah. And that potentially can all be made smarter, but yeah.
The way I think of that is if you remember the like Pareto frontier diagram of like Rust being more efficient and more compile time than Lobster, like Lobster still has that 3%.
Oh yeah.
But consider how much more complicated an example that is. Whereas like in Lobster, you go from having a vector to having a vector. It just has different runtime characteristics.
Yeah.
Whereas in Rust, you now have to say, well, first we have to understand the notion of lifetime variables, which could probably be its own TNC talk.
Yeah, I haven't done a lot of programming in Rust, but I did review the PR that implements all of flat buffers in Rust. And let me tell you, that was pretty hairy in terms of lifetimes. Because like all these Rust objects refer to like this one buffer kind of thing. So they're all lifetime dependent on that buffer. And oh my God, did the programmer have to make some interesting escape hatches to kind of glue it all together. That was very, very hairy. That kind of convinced me, is like, no, there's, even most C++ programmers would start run screaming, I think. So it's a fantastic design, but it's limited in who can deal with it, I think.
Yeah, I think there's definitely a place for it though. Like if you want to express that last mile of performance, like you can do it, you can actually do it and reason about it in Rust, which is actually really cool. Which is still really cool. Like I think there's room in the market for both of the things. But like I'm gonna be rewriting it in Lobster instead of Rust personally. Because I will happily take that 3% performance regression for hobby projects. Thank you very much.
Cool. Any further questions? Wow, we filled almost an entire hour. That's crazy. Thank you for all participating. I love it.
Thanks, Wouter.
For the last 2 minutes, does anyone have a gut feeling to the question I was asking on the previous slide? Is like, do you feel like this is close to like an optimal point, or do you personally see like, would you personally like to see a different optimal trade-off somewhere along that?
Like there's something more in the middle somehow. Like intuitively, like there's something that's going to be like slightly less easy or slightly more performant, but.
Oh, you mean something between current Lobster and current Rust, basically?
And something between current Lobster and C# in terms of like ease. Like on that.
We need more languages.
Yes.
People get on it.
don't have a good reason for thinking that. I just have an intuition.
Could you create a meta language that can be instantiated at any point along that curve?
That would be tricky. It's like you would have to have some kind of way of interpolating the Rust and the Lobster lifetime checkers. That would be an interesting exercise.
Yeah.
Yeah, you want something multi-paradigm at that point.
I guess
where-
for performance, the thing that made me suspicious is the slide about all the choices you made for like what the built-in things do. How did you know that those were the right decisions?
Well, that's the funny thing. Is like I mostly went with like the existing code I have. I have this large body of existing code. So first of all, it's like I'm just wanting to make all that code work without touching as much as possible. And I found like, what this should just do? And I just look at all my existing code and it's like, well, in most cases it wants to do this, so that's the direction I go.
Mm-hmm.
It's extremely incremental, empirical, as opposed to analytical, formal.
But it's also empirical I don't know how big a set of code you have for that. Like I'm thinking of the cases in Chromium where we have two different sets of containers because Blink code is all optimized around the WTF containers, and Chromium code is optimized around the STL containers, and they have different trade-offs. And it turns out that each of them is well fit to the thing that it's well fit to now.
Oh, yeah. But in C++, it's easy to get into this situation because it's just such a nitty-gritty, crazy language, right?
You think that those things are high enough level that's not such a worry?
Yeah, this language is really fairly high level
Yeah.
in most respects. It really is. It's getting to be more low level with some of these features, but it is fairly high level. There's for many things just one way to do things kind of thing. So
Okay.
I don't think it's quite as problematic. Cool. But yeah, it's extremely biased towards, like I said, it's like most of this sample code that I have is all just game prototypes and graphical programs and stuff like that. So it's a little bit biased. Someone might write some completely different and run into all sorts of trouble. I don't know. All right, we're out of time. Thank you, everyone.
Thanks.
Bye-bye.
Thanks, Wouter.
Do I need to stop a recording? Stop recording?
That's probably how.
Yeah, if you just hang up, it's.
Okay.
If it doesn't.